Please remember that Chapter 4 is going to be broken up over 2 weeks, Week 3 and 4. So today we're just going to do Part 1, which is part of Week 3's module. Basically, in this chapter, we're going to be talking about different types of chemical reactions, stoichiometry. There'll be a little bit of supplemental that your textbook doesn't go into as much detail as I would like, so we'll talk about those. I'll also highlight that. But we will have two Chapter 4 videos, one called Part 1, one called Part 2. So the first thing I want to bring up are these different types of reactions. We will go through kind of representing and seeing some of these. You've seen the first two before through like your Chem 152 days and pre-lab, or excuse me, pre-chem classes. And then there's single and double displacement that we'll be talking about in this chapter as well. One thing I want to make note of, we'll talk about the concept of a redox reaction. When we have a single replacement reaction, you should be thinking about a redox reaction. Some double displacement or replacement reactions will also be redox, but whenever we have a single replacement, that's definitely where your brain should go. The other thing we're going to talk about as well is this concept of a precipitation reaction, and a precipitation reaction is a special kind of double replacement reaction. The other thing I want to mention is you will hear sometimes the word single replacement and double replacement. You will also hear single displacement or double displacement. Both of these terms are correct. It's just kind of different ways people say it, but they both mean the same thing and are correct. So before we get into any of our chemical reactions, we need to talk a little bit about solutions, and we need to talk a little bit about water. So I have a really great video. I'll keep kind of pointing out back to the video resources that are in Module 3 at the bottom of the page, or at the bottom of the module. There are some really great animated videos that really do a good job of explaining what we're going to talk about here, especially the dissociation of salt video. The pictures are pretty, but actually seeing the animation of the molecules moving will really help understand this hydration process. So I strongly encourage you to go watch the videos. They are very, very useful for this week. So the first thing we're going to talk about is this concept of polarity of water. Now, we will talk about polarity in so much more detail as we get going, so you don't really need to worry about it too much. But polarity, what we're talking about, something that is a polar molecule or has poles to it. So when I say poles, what I want you to think of is a magnet. Like when you were a little kid and you played with magnets and there was like a north pole and a south pole, right? There were like different charges to the magnet. The same thing can happen with a molecule that has a positive and a negative side to it. And we'll talk about why and how those happen and all that kind of stuff when we get to our chapter on that. But for now, just kind of understand that water is what we call a polar molecule, which means it has these kind of like north and south poles to it. So again, think back to when you were a little kid and you played with magnets. If you had a whole bunch of them and you laid them all out on a table and then you took one magnet and kind of pointed it at different magnets that were on the table, some of them would be attracted and some of them would be repulsed. Same thing happens with molecules. And most importantly, because water is very, very polar, it has a very strong positive and negative to it. So some molecules will be attracted to one side of the water molecule and some will be repulsed by it, and vice versa. So when we look at a water molecule, H2, right, 2 hydrogens, 1 oxygen, H2O, it's in this kind of bent shape. So it's kind of like if you took a little straw and you bent it in half, right? It's in a bent shape. So what ends up happening is the hydrogens are the positive side. So if we took a knife and cut right through here, this chunk where the hydrogens hang out would be the positive side of the molecule or magnet, and the oxygen would be the negative side. Again, we'll go through how we figure this all out and everything later, but for now, that's all you really need to know. And basically, because water is so polar and it has this positive and negative sides to it, it helps things dissolve. And we're going to start using two different words here. We're going to start using the concept of dissolve and dissociate. For right now, we'll just kind of keep moving ahead, but understand that we're going to have two different distinctive words here. This happens sometimes in chemistry. You've probably already seen it in your lab where we talk about accuracy and precision. We know that if you were writing an English paper, you would say, maybe be able to interchange those words, right? This was a very accurate statement. This was a very precise statement. It would mean the same thing. However, in chemistry, those have two very different meanings to them. You may think, in the general sense, that the word dissolve and dissociate mean pretty much the same thing. But when we're talking about it in terms of chemistry, they have different connotations to them. So let's talk about the process of hydration. You've probably thought of this word before and heard this this word before in like a Gatorade commercial, right? Where you're told to hydrate. And what happens when you hydrate? You're adding water to yourself, right? You're working out. It's hot out. We're still in a heat wave. I'm melting here in Poway. So you have to drink a lot of water. You have to hydrate yourself. Compounds can be hydrated as well. Experiment 1C that you've done in your lab is about hydrated compounds, right? So that's where water molecules are being added. This is a little different. So this is going to be the process by which water dissolves things or dissociates and breaks them apart. So what ends up happening is we're going to use an ionic compound here for our example. The example that's in that animated video is table salt. So we'll pretend that this is some table salt, okay? So that's NaCl. So the gray balls are the Na and the green balls are the Cl. I will make a note real quick. I do use a lot of color coding throughout all of my videos, my presentations, my lectures, everything like that. If you are someone who experiences difficulty with color distinguishing problems, so if you're colorblind or something like that, please let me know so that I can change the methodology that I use in terms of how I kind of distinguish things. I can do it. I just need to know because as of right now I'm going ahead with the color coding. If that is an issue for you, please let me know and we can adjust for that. Okay, so here's our table salt, our NaCl. Think of this as like a hunk of NaCl, right? And I'm going to plop this into a glass of water. Now, if you've ever put salt into water, you all have the experience of knowing that this will, up till now, you thought dissolve. It's technically going through a process of dissociation, but for right now, let's move ahead. We have a whole bunch of water molecules. We know in like a glass of water, there's billions and trillions and gazillions of water molecules. And we know that an ionic compound like NaCl has positively charged and negatively charged ions in it. So just like we talked about with the magnets before, right? When you were playing with magnets as a little kid, the negative side of the water is going to be attracted to the positive cations. The positive side of the water molecules are going to be attracted to the negative anions. So what ends up happening is as this ionic compound hangs out in the water, water molecules begin to surround it, and they kind of arrange themselves in a way where the positives are attracted to the negatives and the negatives are attracted to the positives. And what we can see happen is all the negative oxygens will surround a cation of sodium in this case. And they'll surround it because they're all attracted to it, and they go, hey, sodium, we're way cooler than the rest of the salt molecule, so you should come hang out with us instead of the salt molecule. And then the sodium goes, okay, and so the sodium molecule leaves, or excuse me, the sodium ion leaves. The same thing happens with the chloride anion. All the positive ends of the different water molecules begin to surround the negative anion. And they surround it, and they through attraction of the electrostatic attraction, right, the magnetic attraction between the two different charges, and they say, hey, chloride ion, you should come hang out with us instead of being with this lame salt molecule. And the chloride ion goes, okay. And then this keeps happening over and over again, right? As each layer, the outer layer is exposed to more water and gets removed, inner layers are further exposed until it completely breaks apart the entire NaCl molecule. Or crystal structure of this NaCl. Again, the video does a very nice job of actually showing the dynamics of this. So when we have an ionic compound that breaks apart in water, we call this dissociation, okay? So this is an important distinction. When we have a covalent compound or a molecular compound, for example, let's say glucose, like table sugar, that would dissolve in water. Ionic compounds like NaCl will dissociate in water, okay? Molecular compounds, covalent compounds, whatever you learned how you call them, when they break apart in water, that is called dissolving. Ionic compounds, when they break apart in water, it's called dissociation. And now we're going to start talking about what the difference is here, okay? So dissociation, hydration, right? This process of adding water to something will cause salts, we're saying ionic compounds, right? Salts, not just table salt, but any salt, to dissociate, right? The strong forces present among the positive and negative ions of the solid are replaced by strong water ion interactions. So, right, that's where we're saying the waters surround the cation and they say, hey, we're cool, come hang out with us. That's the interaction that we're talking about there. These strong water ion interactions. Now, dissociation is a little bit different from dissolving. Dissociation means that when an ionic compound is in water, we no longer have that ionic compound. I don't have the compound NaCl anymore. I have Na pluses and Cl minuses hanging out in water. NaCl, the molecule, the structure, the bound compound together does not exist. That's what we mean by dissociate. They're their separate own thing now. When something dissolves, for example, sugar, right? This is a covalent compound, C6H12 O6. We have this covalent compound. We know sugar dissolves in water, but what ends up happening is the sugar, right? Like the cube of sugar that you throw in water, that's a crystal structure of a whole bunch, right? Moles and moles and moles of sugar molecules hanging out together. And all that happens when something dissolves is the sugar molecules hanging out together get separated, and now we have individual sugar molecules hanging out. But it's still a sugar molecule. The carbons are still bound to the hydrogens, which are still bound to the oxygens in that one molecule. They're just not hanging out and associated with other sugar molecules. That's dissolving something. Dissociating something means we have actually taken the starting material and ripped it apart. It no longer exists. It's like when One Direction broke up. We ended up with a whole bunch of, Harry Styles doing his own thing, right? They all did their own thing. They no longer existed. Or what the heck are the brothers? I can't remember their name. I don't know. But anyways, sorry, bad pop culture references there. We will see more of this dissociation as we go through this. But again, just to reiterate, this should be something you should be writing down in your notes. Covalent compounds dissolve. Ionic compounds dissociate in water. So, water as a solvent. What does this look like in terms of a chemical equation? Right? This hydration, right? The dissociation. Here's another ionic salt. We have ammonium nitrate. We know ammonium, this is a positive polyatomic ion, a cation, and that nitrate is a polyatomic anion. Together, when they're outside of water, they're a solid. When water is added, or if we took a beaker of water and poured this into it, we have full dissociation occur, okay? Ionic compounds, when they dissociate fully, which means we no longer have this solid. We just have a whole bunch of the ions floating around surrounded by waters. So we went from the state of matter being a solid to aqueous. So make sure you're comfortable with what aqueous means, right? That's a solution. Now, there are varying degrees of solubility of these ionic compounds. Not every ionic compound will dissolve in water, and that's fine. These solubility, it's kind of like a spectrum that the solubility is on. Some things are only slightly soluble, some things are definitely not soluble at all, and some things are very soluble. You will not need to necessarily memorize these solubilities. You will have access to solubility charts, and you'll need to know how to read them to be able to help you. Again, we do see many examples of non-ionic substances that dissolve in water, but what they are doing is dissolving. They are not dissociating. So here's an example of ethanol, which is the alcohol that you can drink that's found in like spirits, wine, beer, vodka, things like that. Ethanol. This is the one that's safe to drink. Methanol is the one that is not safe to drink. Again, only if you are 21 and older. So what we're talking about here is this is a covalent compound, right? This is not ionic. There's 2 carbons. There's 6 hydrogens and an oxygen. There's no ionic compound, metal, non-metal going on here. But we know that water will dissolve this. And we see that it's an interaction because they're both polar. We will learn more about this concept of like dissolves like later in the semester. So what happens to our ionic compounds once they are dissociated in water? One of the ways we kind of describe the solutions are whether they are strong or weak electrolyte solutions. Before we can talk about that, I just wanted a quick review for you folks. This is a little bit of a step back from like your prereq days, but the concept of a solution versus a solute versus a solvent. You should be able to describe and give a definition of all 3 of these. A solute, and again, if you need help with this, the additional worksheets are very good and useful for this. A solute is the thing that is dissolved into the solvent. Typically, we describe this if you were talking about salt water. We would say that the NaCl is the solute, the water would be the solvent, and that the solution would be the salty water. Okay, so the solution is a homogeneous mixture, right? Composition can be varied and changed, and different amounts of solutes can be dissolved in the solvent. But it's the mixture, the solution is the mixture of the solute and the solvent. The solute is the thing that is getting dissolved. The solvent is the thing that is doing the dissolving or dissociating. The more technical definition of these 2 is the solute is the thing we have a less amount of. The solvent is the thing we have a greater amount of. The reason we do this is because sometimes it's not clear which is dissolving into which or which is dissociating into which. And so we need to look at amounts that are present of each of these. Please keep in mind that for the most part, we will be dealing with solutions where it's like a solid in a liquid or a liquid in a liquid. Those are the most common. But a solution could be a gas in a liquid. A solution could be a gas and a solid. A solution could be 2 gases. A solution could be 2 liquids. So it becomes less clear as to what's going on. It's not a solution, by definition in chemistry, isn't necessarily a liquid only situation. So that's why we have this definition of a solute as something that we have more of, or a solute is solute is something that we have less of, and the solvent is something that we have more of. So what is the strong and weak electrolyte that we're talking about? This is kind of how we define these solutions that get dissociated. So you may have heard of electrolytes before. Again, typically like a Gatorade commercial where they tell like you that you can replenish your electrolytes. Unless you are running an Ironman or sweating so much that you are losing all of the salts in your body, you probably don't need to replenish your electrolytes while you're working out. You just need some water. Gatorade is just very fancy, high caloric, very colored, sweet, salty water. That's essentially what it is. Sounds kind of gross when you put it that way, but that's what Gatorade is. So electrolytes are a solution and their ability to conduct electrical conduct, like an electrical current. So a strong electrolyte would be something that is able to strongly conduct electricity. You can have a moderate to a weak electrolyte or a non-electrolyte. And so we're going to go through the differences between these. if we have a lot of ions present in our solution, positive ions and negative ions, it would make sense that the electrons in the electrical current would be able to easily jump around through the solution, hence very high electrical conductivity. If we have a couple sparse ions around, the electrons might be able to flow through it a little bit. If there are no ions present, there's nothing for the electrons to jump around through. So that we have strong electrolyte, weak electrolyte, non-electrolyte. So, those three types of electrolytes. A strong electrolyte comes from, is a solution where the solute dissociates 100% in water, or the solvent. So the example we gave earlier of NaCl, table salt, this dissociates 100%. We get no more NaCl exists when it's in water. We have Na plus and Cl minus. A weak electrolyte will only partially dissociate. What we mean by that is we may have small amounts of dissociation occur, but most of the molecule is going to stay together. So we only have a few ions floating around in solution, whereas when we have 100% dissociation occur, we have many, many ions. And then lastly, a non-electrolyte will be something that does not dissociate in water. They only dissolve, which means there are no ions in water. An example of this would be table sugar. One of the concepts I want to bring up that a lot of students struggle with is the idea that pure water, pure H2O, pure water, is a non-electrolyte. It does not conduct electricity. Now, you may be saying, Dr. Sardo, there's a whole reason you're not supposed to go outside and be in like the pool when there's like a lightning storm. And you're absolutely right. You should never do that. That's because the pool, the ocean, a puddle outside, they are not pure water. The ocean is salt water. It's a very, very good electrolyte. Pools have lots of cations and anions in them as well. Again, very strong electrolytes. Even a puddle outside. Again, there are lots of impurities in there that are contributing to it being a good electrical conducting solution. So, when we're talking about strong electrolytes, let's kind of dig deeper into each of these types of solutions. Typically, strong electrolytes are formed from soluble salts. So again, our example there was NaCl, or any other salt that will dissociate 100%. This will also happen with strong acids and strong bases. We'll define what a strong acid and a strong base is in a little bit. But these three types of solutes, when hydrated, will produce strong electrolytes, which means they produce lots and lots of ions in the water. So a strong acid. Many times, again, we talked about this earlier, the idea that in chemistry, words we use in chemistry have different meanings in our everyday lives than they do when we're talking about them in chemistry. Most students think that when they hear the word strong acid, we're talking about a very, very dangerous acid. And if I said a weak acid, you'd be like, oh, well, that's not as dangerous, maybe not as corrosive. That's entirely false. A strong acid and a weak acid has nothing to do with its ability to be corrosive, and has everything to do with whether it's a strong electrolyte or a weak electrolyte. Just for your reference, the weak acid, HF, is much more corrosive and dangerous to you than something like HCl. So again, the word strong and weak for acids and bases has no basis in how corrosive it can be and how dangerous it can be. And it's actually a definition of whether it's a strong or weak electrolyte. So let's talk about our strong acids. Some examples I have here: HCl, HNO3, H2SO4. What we're talking about is they behave as strong electrolytes in water when they're dissolved. HCl, when it is dissolved in water, makes H plus and Cl minus. That's really what we have. When we have, when you go to lab face to face and there's a beaker of HCl aqueous, right, in the bench on the hood. What's actually in there, if we could have like some sort of microscope that could look at it on the molecular atomic level, we would see a whole bunch of H's surrounded by water and a whole bunch of Cl's surrounded by water. This guy is not existing bound together in there. Same with this one, same with this one. That's because they dissociated 100%. All of it exists like this now, which means we have a ton of ions present in our solution, which means it will be a strong electrolyte, a good conductor of electricity. So, we'll talk a little bit more about acids and bases later on, but again, I just want to go through some basics of, what characterizes an acid in general. So I have this general equation here. HA is just representing any acid. As typically we will see it, there will be the acidic hydrogen, or the proton that will go away. And we can represent it like this. You could pretend this was HCl, HF, H2SO4, right? All the different acids that we know, HNO3. The A is just a filler. So HA plus water will yield H3O plus and A minus. And now you may be going, what the heck is H3O plus? Well, A minus came from HA, right? So the H and the A broke apart. H2O becomes the H3O plus. When the HA breaks apart from the A, we have an H plus floating around hanging out by itself. H plus is, we could pretend, is like very insecure and doesn't like to hang out by himself. So he's going to go over the water and be like, hey, can I come join you guys? And the water says, sure. So they become H3O plus. But basically this is just representing a free H plus and an A minus, right? Plus and minus. Ions. Strong bases will also dissociate 100%. Okay, so again, strong acids and strong bases dissociate 100% in water. I'll say that again. Strong acids and strong bases dissociate 100% in water. You should be writing that down in your notes. When we have a base, again, it will completely dissociate. Most of the bases that we'll see will contain a hydroxide. There are other bases that we'll talk about, but these are the very common ones that you would see. So for example here, potassium hydroxide is a solid. When it's exposed to water, we dissociate 100% and we get potassium cation and hydroxide anion. Therefore, a very strong electrolyte. Weak electrolytes. So again, remember, weak electrolytes are things where we only produce a small amount of ions. So most of the compound will stay together and not break apart in water, but a couple will. So we get what we say a small degree of ionization in water. And this would be things like weak acids and weak bases. So again, remember, weak acid, weak base has nothing to do with corrosion and everything to do on whether or not it can produce a strong or weak electrolyte. So an atom that produces an H plus ion, right, the acidic hydrogen, is usually listed first when we do this. So here we have acetic acid. If you don't know what acetic acid is, if you've ever had a pickle or had vinegar or salad dressing, you have ingested acetic acid. Acetic acid is vinegar. The vinegar that you and I eat is a very diluted version of it. The acetic acid that we use in the lab, a very concentrated version of it. But still the same thing. So when I have acetic acid and is exposed to water, we do get some of that H3O plus. Some of that H plus hangs out, but we also get the anion of that, right? But this is important. Look what we have here. You may have never seen this kind of yields arrow before. This kind of arrow is a little different in terms of the fact that it's showing us that this reaction can go back and forth. Up until now, you've probably seen chemical reactions where the arrow goes in one direction. It's kind of like a one-way street. Cars can only go one direction. In this case, we have a two-way street. While this reaction is occurring in this direction, and we're losing the hydrogen off the acetic acid and it's making H3O plus and the anion, this direction is also occurring, where this and this are combining, giving us H2O and acetic acid. So, what ends up happening is we don't have 100% dissociation. We get a little bit of the ions present, and we get a lot of the acetic acid present just hanging out in this form, which means there's no ion there. So we only have a few ions present, which would make it a weak electrolyte. So here's just an example to kind of help show what we're doing here in terms of a molecular level. Again, this would be if you could look at what happens, through a special microscope or something as we poured our different acids and bases into water. Here we have NH3, which is a weak base. We can see that in our beaker, only a few ions are present. Same thing would happen in our case over here with our acetic acid, where we only have a little bit of the ions present. So these are both examples of weak electrolytes from weak acids or bases dissolving in water. The last kind of aqueous solution is a non-electrolyte. So again, these are going to be examples of things that are covalent compounds, molecular compounds, things that won't break up at all into any ion. They just dissolve. They don't dissociate. Okay? But again, that difference between dissolve and dissociate you should be comfortable with. So when we're talking about solutions, one of the things we use a lot to kind of explain, describe a solution is its concentration. I even said it earlier when I was talking about the acetic acid, that the vinegar that you buy at the grocery store that you ingest is a much more diluted version of acetic acid than what we use in the lab. Obviously, one is delicious on salads, and the other will be very harmful to you. So concentrations can be very, very important. And so in chemistry, when we're talking about concentrations, we're going to be talking about the concept of molarity. The unit that we use for it is big M, capital M. Little m means something different, so you do need to be conscious about which m you're talking about. But molarity stands for moles of solute. Again, you need to know the difference between solute, solvent, and solution. Moles of solute over liters of solution. Again, please go do your reading. I am not going to discuss dilutions in these lecture slides, but you do need to know about dilutions. If you have a question about dilutions, please contact me. But you are expected to be reading about those and understanding it. A solvent versus a solution. Again, we're telling you here that molarity is liters of the whole solution, not the solvent. If the solute was a solid, then the volume of the solution is the same as the volume of the solvent. But let's say, for example, we had a liquid solute, and we had 2 milliliters of our liquid solute and 2 liters of our, we'll do liters, 2 liters of our liquid solute, and we had 8 liters of our liquid solvent. That would mean that the total liters of the solution would be 10. So it's something that you need to be conscious of and aware of as we move through it. These are the types of chemical reactions that we're going to discuss this week and into next week. Precipitation reactions we'll tackle during this slide presentation. We've touched a little bit on acid bases, but we're going to go into much, much more detail with that next week. Same with oxidation reduction reactions, also called redox reactions, as well as your book kind of skims over the concept of gas-forming reactions, so we'll talk about those as well. So the first type of reaction we're going to talk about is a precipitation reaction. A precipitation reaction is kind of visually very stunning to watch because what ends up happening is it's when two solutions are mixed together and they form a solid. So pouring two liquids into the same beaker and it produces a solid. You're right, that's pretty neat. That solid is called the precipitate. Okay, a lot of students kind of forget that when we're talking about a precipitation reaction, the solid that forms is the precipitate. And what that means is it's a solid that's insoluble in the solution. Typically the solutions are aqueous or water, so they're things that are insoluble in water. So here we have an example. When an aqueous solution of potassium chromate, that's this guy right here, is added to the colorless solution of barium nitrate, we get barium chromate, a yellow solid that forms a precipitate. So that sits at the bottom. So when we pour these, if we took both of these beakers of these solutions and we poured them into a new beaker or poured one into the other and mixed them around, we would produce a yellow solid. So what's really going on there, right? Let's go back to our chemical equations and kind of talk about what's going on. We have aqueous potassium chromate. Here's our aqueous potassium chromate. And our barium nitrate right here. Okay, when these two, right, this is the yellow beaker, this is the clear beaker, colorless beaker. When those two are mixed, they produce products. Let's think about what these products would be. Well, we know that the potassium's the cation, the chromate's the anion, the barium's the cation, the nitrate is the anion. We know that two anions couldn't mix together, and we know that two cations couldn't mix together, right? Two positives, two negatives, they're not going to mix. We want to get a positive with a negative. So the only way we'd be able to do that is to kind of switch dance partners. The potassium would have to go with the nitrate, and the barium would have to go with the chromate. When we do this, right, we could say, okay, well, this is an ionic compound, and this is an ionic compound. And they're an aqueous, which means it's in water. And I know that you know that I know, kind of like a secret little language, that when I see this, this really means this is going to dissociate. I'm going to have two potassium cations and one chromate ion floating around in my water. That's what's really happening here. Same thing with the barium nitrate. I get one barium nitrate and I get I get one barium cation and two nitrate anions out of this. So this is what we typically see when we write it out. But this aqueous with an ionic compound is kind of a secret language. We need to start thinking of it like this. That this is shorthand. And this is me saying, the secret language is telling me all of this is actually in there. And that when we mix the potassium with the nitrate and the barium with the chromate, those would be our products. And it looks something like this. So here are those solutions mixing together. Here are the solids that are produced. This is what it actually looks like, right? So this is on like that special magnifying glass that we talked about, right? Or special microscope that we can see molecules with. In real life, if you were in the lab, it would look something like this. Those two mix together, and the solid sits at the bottom. So I told you that we have solubility charts that help us understand which ionic compounds are soluble in water and which aren't. This is an example of one from your textbook. I will encourage you to go look at the one that's in Cengage. That's the one that will be on your tests and quizzes. I would encourage you very, very strongly to go print that out. Print out the solubility chart that is provided in Cengage. And you can make notes on it and everything like that, but go print it out because during tests and quizzes you won't be able to open it. So we have this understanding now that we can do these precipitation reactions, which are a special kind of double displacement reaction, and that we know that when we have solutions that they could be strong electrolytes, they could be weak electrolytes. Now we're going to start finding out that there's different types of equations we can use to describe this reaction as it's occurring. The first is a formula equation. Basically, this is the one you know already. Whenever you've written a chemical equation, it's been the formula equation. So this includes things like balancing, states of matter, all that kind of good stuff. It's written in that secret language where we would have to break it apart and go, yes, I know that you know that I know that when I see NaCl aqueous, what that really means is Na plus aqueous plus Cl minus aqueous. Then we have the complete ionic equation, and this is where we break up that secret language and we write it out in full ions, all the ions that are present. And then lastly is the net ionic equation. If you've ever been employed and you have your gross pay versus your net pay, you know that your net pay is what you get to bring home after taxes and all that kind of good stuff. So things have been taken out of your pay. A net ionic equation is the same thing. What we call spectator ions have been taken out of the reaction. Spectator ions, just as the word suggests, are things that just kind of hang out and watch. They don't participate in the chemistry. They're not doing any of the work. So we're going to do an example problem to go through this concept of writing these different chemical equations. So here is our problem. Aqueous potassium hydroxide is mixed with aqueous iron 3 nitrate to form a precipitate of iron 3 hydroxide and aqueous potassium nitrate. Whew! Alright, so if you've noticed, we've kind of graduated at this point to no longer using formulas. This is why you had nomenclature on your first exam and your quizzes and stuff. We are expecting that you would know what the formula is of potassium hydroxide, what the formula is for iron 3 nitrate. You will need to be able to do this. So, as I talked about, I'm going to be using color coding to kind of help keep track of where everything is. If you have an issue with this, please let me know. So the first thing I'm going to do is break up my problem so I can identify all the bits and pieces of it to help me write out my formula equation. So I'm going to go and say, okay, potassium hydroxide, aqueous, you must have states of matter. If you do not have states of matter, it is wrong. You will get points off. Potassium hydroxide plus iron 3 nitrate yields iron 3 hydroxide, and potassium nitrate. Now, just like always, whenever we have a chemical equation, the first thing we should think is it balanced? Is this equation balanced? We can't do anything else with this until we know if it's balanced. So go ahead and look at it for a minute. Figure out if this equation is balanced. It is not. So we have to go and balance it. Easily done. This is a relatively simple balancing equation in terms of the fact that we now have to have a 3 in front of the KOH and in front of the KNO3. Alright, so now we're balanced and we can move forward. The formula equation is what we are familiar with, right? This is that secret language where when I see an ionic compound, an aqueous, I actually have to go, yes, I know that you know that I know. This is really K plus and OH minus. So go ahead, I would encourage you to pause the video here and write out the complete ionic equation. When we write out the complete ionic equation, we need to keep our balance equation still present in it. So if I have 3 KOHs, that means I have 3 K pluses and 3 OH minuses. I have my iron 3 plus. How do I know it's 3 plus? Because it told me it was 3 plus. And the 3 here represents 3 nitrates. So I actually have to have my 3 nitrates here. Again, all aqueous. On the product side, we have iron 3 hydroxide. Iron 3 hydroxide, we're told, is the precipitate, which means it's the solid. We don't break up a solid. Solids stay solids. They're insoluble in the water. So this is the only one that doesn't break up. Then we have KNO3, 3 KNO3s. Those are aqueous again. That's the secret language. 3 Ks, 3 NO3s. So this is our complete ionic equation. Everything has been broken out into its ions where appropriate. Next step, I want you to try and identify in this complete ionic equation what you think would be spectator ions. Remember, spectator ions are the things that don't do any chemistry. They just sit and watch. So they're the things that go in the same way they come out. So again, pause the video here and try and identify the spectator ions. Spectator ions in this case would be the potassium and the nitrate. So we have 3 potassiums go in, 3 potassiums come out, 3 nitrates go in, 3 nitrates come out. They didn't contribute to the chemistry. So those are actually removed when we go to write the net ionic equation. So go ahead, pause the video one last time, and write out your net ionic equation. Our net ionic equation for this chemical reaction would be 3 OHs aqueous plus our iron 3 plus aqueous, yielding FeOH3 solid. It doesn't really matter if you put the iron before the hydroxide. That's neither here nor there. So this is an example of a precipitation reaction. Do you see it? An aqueous plus an aqueous yielded a solid. All right, this is the end of our week 3 video. What should you be working on moving forward? As I mentioned, chapter 4 is big and it's a lot of new material, so we're breaking it up over 2 weeks. Homework number 5 for chapter 4 is going to be due at the end of week 4. Do not fall into the trap of waiting to the last minute to do this homework assignment. It is long. It is meant to take 2 weeks. Okay? Don't wait till Saturday afternoon on week 4 to go start this. Okay? You will be stressing yourself out. As we move forward through week 3, you should be reading chapter 4. This slide material covered sections 1 through 6 of chapter 4. You should start the homework. We have not covered all the subjects that are in the homework set. So if you see a problem and you're like, I don't think I've ever seen this before, it's entirely possible you haven't seen it yet. So, do the ones you can do, start working on it. But the rest of chapter 4 will happen in week 4. I've opened up both weeks, starting at the beginning of week 3. If you finish week 3 early, you can move on. But don't try and rush and bang it out. You need to actually understand and internalize this material. Ramming through it in one go is not going to give you time to reflect on it and understand what's really occurring there. So please make sure you're giving yourself the adequate time you need to be able to really comprehend the material. If you have any questions with week 3, let me know. I'll be available for email. This week 3, once you have taken your exams, I'll be reviewing those, going over the materials in there as well.